The first fundamental theorem of calculus relates the definite integral of a function and the antiderivative of the function. Recall that the definite integral of a function is defined geometrically as the area under its graph and is a number. On the other hand, the antiderivative of a function is a function whose derivative is the given function. How does the fundamental theorem relate these two? Well, it says that the definite integral of a function small f from a to b is equal to its antiderivative, big F, evaluated at the upper limit b minus big F evaluated at the lower limit a. Notice that, as you have already seen in the last problem, even though the antiderivative of a function is defined only up to a constant, the quantity on the right-hand side of the equation, f of b minus f of a, does not depend on which antiderivative of small f is used. Let us do an example. Let us evaluate the integral of x squared from 0 to b. Here, little f is x squared. The first fundamental theorem says that this integral is equal to any antiderivative of x squared evaluated at the upper limit b minus the same antiderivative evaluated at the lower limit 0. Now, an antiderivative of x squared is x cubed over 3. So the integral is x cubed over 3 evaluated at b, which is b cubed over 3, minus x cubed over 3 evaluated at 0, which is 0 cubed over 3, which is 0. So the integral is equal to b cubed over 3. This is the same as the answer we got last time using Riemann sums. But remember how long and laborious the whole computation was? With FTC1, we don't need to use Riemann sums anymore. All we need to evaluate a definite integral is to find an antiderivative of the integrand and evaluate it at 2 points. Finally, let us introduce a notation. We denote the difference f of b minus f of a by f of x, then a vertical bar on its right, and b placed next to the top of the vertical bar, and a placed next to the bottom. Notice the ordering of a and b. The top value is the one that comes first in the difference. Let us use this notation for our example. The integral is equal to x cubed over 3 evaluated at b, placed at the top, minus evaluated at 0, placed at the bottom. This notation is convenient because we can avoid copying big F twice. So now I'm going to erase this difference in terms of f and replace it by our new notation. The notation is especially useful if big F is complicated. From now on, we will use this notation as much as possible. Let's now evaluate some integrals using our new computation tool, the FTC1.